I'm Dr. Jeff Groh, and this is the history of the Big Bang. The term Big Bang was invented by Fred Hoyle during a BBC broadcast in 1949. More on this later. Einstein published 4 papers in November of 1915 on the general theory of relativity, or at least he submitted them to the Annals of Physics. There was a March 1916 paper that came out later. We're going to show some elements of that. This is part of that March 1916 paper, and it refers to this, I'll put it in English, and it refers to the advance in Mercury's perihelion, something that had been observed since Leverrier some 60 years earlier, and had been an outstanding problem in astronomy for all of those years. He shows, in particular in his third paper from November of 1915, and also in this paper from March of 1916, that his theory of gravity exactly resolves that outstanding problem of astronomy. It turns out that the problem was Newton's theory of gravity was wrong, and Einstein's theory of gravity is right. Since then, there have been many experiments that have shown that Einstein's theory works better for observations within our solar system than Newton's theory. So Einstein's third paper of November of 1915 approximated his gravitational theory's equations of motion as applied to the planet Mercury. In his fourth paper of that month, Einstein modeled gravity as curvature, giving his field equations. Now, in 1919, Arthur Eddington verified Einstein's prediction that light bends around the sun. Einstein's field equations imply that massive objects curve space-time, which causes light to bend around those objects, and this was observed as early as 1919 by Arthur Eddington. Since then, many other evidences have been found showing that Einstein's theory is very accurate, at least for all observations that are within the solar system. Take special note of the date that this paper by Carl Schwarzschild was published, 13th of January, 1916. This is the first actual exact solution to the Einstein equations ever found. When Einstein published his field equations, he had no solutions. Schwarzschild, in January of 1916, hot on the heels of Einstein submitting his theory to the Annals of Physics, Schwarzschild publishes an exact solution. It's for spherically symmetric empty space, and it ends up having a black hole. Also, make special note of the day that Schwarzschild passed away. He died the 11th of May, 1916, a very short time after he published this paper. So Schwarzschild's solution was spherically symmetric empty space and had a black hole, a Schwarzschild radius, the radius of a sphere that light cannot escape from, making it a black hole. Everyone, including Schwarzschild, thought that this was a non-physical solution to Einstein's equations, that is, until the famous Oppenheimer-Schneider solution in 1939. It was soon discovered that Einstein's equations make the universe non-static. What does that mean? Masses attract other masses. Since mass is proportional to curvature, space should attract itself. So space should collapse in on itself, unless it's expanding, of course. If the universe starts out not expanding, just sitting there, not expanding or contracting, it's just sitting there, then it will contract and eventually vanish in a big crunch. Let me give you an illustration. Here I've taken the Hubble Deep Field image and wrapped it onto a sphere. I can make this collapse in on itself in a big crunch. Here we go. And the universe is gone. There's nothing left. If, however, the universe is expanding, then it should have started in a big bang. Expanding spaces should expand at slower and slower rates due to this self-expansion, which, by the way, is contradicted by recent observations from the 1990s. So here's the Big Bang. There's the universe, it's back. If space should ever stop expanding, then it must collapse in on itself in finite time, and the universe should vanish at that time. And so in this case, you would have both a Big Bang and a big crunch. So let's see that. Here's the Big Bang followed by the big crunch. So the universe expands to a maximum point and then contracts and vanishes. The implications of Einstein's theory are either the end is nigh, there's a big crunch, and this spells the end of not only all matter, energy, momentum, and space, but also time itself would end. Or the universe had a beginning, a big bang, or both, a big bang and a big crunch. So the universe coming into existence violates conservation of mass, energy, and momentum. This is a big problem for scientists to address. One way of thinking about it is to look at the so-called Friedmann equation with a delta function. The Friedmann equation models an expanding universe. I'm going to model this to begin with a universe that is just flat and level, is just sitting there with no mass, energy, or momentum in it. It's not expanding or contracting. It's just an empty space-time. But I'm going to hit it with this little red pulse here of what is called a delta function force. Hitting the universe with this delta function force, all mass, energy, and momentum is created, and the universe begins expanding at that point in time. One of the problems with such a conception is, why would there need to be an empty universe if there's no matter to occupy it? And so it makes more sense to put that non-conservation event at the Big Bang, at the start of the universe itself. Here I've put that red delta function source at the Big Bang, and from there the universe expands and all mass, energy, and momentum are created at that instant. By the way, normally when people who study the general theory of relativity solve the Einstein equations, they assume that those equations don't have any strange kind of phenomenon like a delta function source, in which case they can't get these solutions to exist all the way back to t equals 0 when the Big Bang occurred, only to t values that are positive. But you can get the solution all the way back to t equals 0 if you throw in this delta function source for all mass, energy, and momentum in your spacetime. A Big Bang requires an appeal to non-mechanical, non-physical forces outside of space, time, mass, energy, and momentum that brought everything into existence. This is a big problem. The Big Bang is the ultimate non-conservation event. This makes us think immediately, in the beginning, God created the heavens and the earth, Genesis 1:1. Well, Einstein had a problem with this himself. And so by the 8th of February 1917, Einstein introduces his so-called cosmological constant. You can see that here as the lambda in the equation 13a. He's throwing in this lambda. Lambda is his cosmological constant. He's doing this because by adding this cosmological constant, he can add a force to the universe which can keep it from contracting or expanding. He can make the universe static again. So the static universe is restored, but there's just one problem. It's not stable. Any small variation in the value of that lambda will cause the universe to expand or contract. So this is great. Einstein was able to introduce this cosmological constant Without it, the universe is not static. With the cosmological constant, the universe is unstable. And so you still have a problem. It's like trying to balance a pencil standing straight up on the palm of your hand. It's very hard to do. Einstein said, "Since I introduced this term, the cosmological constant, I had always a bad conscience. I am unable to believe that such an ugly thing is actually realized in nature." By 1921, people were already resorting to non-Riemannian geometries. You can consider Weil or Eddington and others to try to get around all of these issues. Let me illustrate the Big Bang like this. Suppose that the universe, the spatial part of the universe, is pictured as a circle. Here I've drawn a surface, and each horizontal cross-section is a picture of the entire universe at one particular time. So at each time, the universe is a circle. As time goes on, that circle gets bigger and bigger and bigger. So time is on the vertical axis here. Now it turns out, if the universe is expanding, then as time goes on, the circle should have a larger and larger radius, and the time vector field is tangent to this surface. The time vector field will be as depicted here. There'll be vectors on the circle, but pointing in the direction that the universe is expanding. The time vector field is tangent, and as time increases, the time vector field moves up. You can see that the later cross sections will have those vector fields a little bit higher, but as you go backwards in time, the time vector field is increasingly divergent. What is a divergent vector field? Here's a picture of a diverging vector field where the vectors are all moving apart. That's as opposed to a converging vector field where the vectors are all coming in together. The only problem you have with a diverging vector field like this is at the origin, because you can't continuously extend this vector field any further than through the origin. It won't be continuous anymore. And that's exactly what happens to the time vector field on space-time at the origin, at the Big Bang. The divergence of the time vector field goes to infinity as time goes to 0 from the right as you go towards that Big Bang. So time can't be extended any earlier because you can't extend that vector field anymore. Time has no meaning earlier than the Big Bang. This brings us to the cosmological argument. Everything that has a beginning has a cause. The universe has a beginning. Therefore, the universe has a cause. Whatever you appeal to as the cause of the universe must be outside of space, time, mass, energy, and momentum. In other words, the cause of the universe is outside of all known physics and mechanics. Choose your favorite myth. Quantum fluctuations are just an unscientific myth. Now, Alexander Friedman in 1922 published a cosmological model, and actually it was 3 solutions to the Einstein equations. He assumed that the Einstein equations would have maybe an isotropic, homogeneous mass distribution. So mass is distributed throughout the universe in an even way, and it will look the same from every perspective. He found 3 solutions, one with spatial curvature positive, one with negative, and one with 0 curvature. These all have Big Bangs. He published also his famous Friedman equation, derived from the Einstein equations, governing the rate at which the universe expands. Now, all of his solutions have a Big Bang. Friedman had 2 major disadvantages. He was Russian, and he died very young. Look at that, he died in 1925, just 3 years after he published his famous exact solutions to the Einstein equations, having each a Big Bang. By 1923, Arthur Eddington has published Slipher's data from the Lowell Observatory showing most galaxies, which at the time were thought of as spiral nebula, are receding on average 600 kilometers per second. He doesn't give distances to each of these galaxies, so he doesn't get the Hubble relation. Georges Lemaitre, in 1927, he rediscovered Friedman's solution to the Einstein equations. In discussions with Edwin Hubble and using his data, Lemaitre predicted the Hubble relation. And here you have that. He had certain disadvantages. He was Belgian. He was a priest. His publication was obscure and he was quite young. However, he did directly meet and interact with Albert Einstein. His 1927 paper used the cosmological constant. So, for example, this comes directly from his 1927 paper, and he has that, it's a square root of lambda, but there it is, lambda, the cosmological constant, right there in his paper. He does this in order to try to avoid a Big Bang. So even in 1927, despite the fact that Georges Lemaitre has rediscovered the Friedman solutions, he's trying to avoid that by keeping that cosmological constant around. So Edwin Hubble showed that the spiral nebula are in fact individual galaxies, and by 1929, he developed a linear relationship. He showed that there was a linear relationship between the distance from where we are to each of these distant galaxies and how fast those galaxies are moving away from us. He used linear regression. In January of 1931, Einstein actually went to visit Hubble at the Wilson Observatory looking through the 100-inch Hooker telescope. This is the actual Hubble data on the left, and on the right I've plotted the distance to galaxies versus the recessional velocity. You'll note that I've also given a least squares line of best fit and calculated the correlation coefficient to be 0.78. So it looks like the further away you go, those galaxies are moving faster and faster away from us. Now, why is that true? It's not that galaxies further away from us are actually moving faster away, but the light that's coming from them has had more time in transit, and the space in between has been stretching so that the light is red-shifted, making it look like the galaxies are moving faster away from us. The longer the light is in transit, the more the space in between has stretched, the more that light is red-shifted, and then it looks like those galaxies further away are going faster away from us. In 1929, Robertson publishes a paper describing all classes of static spacetimes and shows that they are in classes that are non-static. So, in other words, those static spacetimes are always going to be unstable. Georges Lemaitre predicts the early universe may be observable as cosmic ray radiation, which was wrong. It's microwave radiation. In 1934, Richard Tolman showed the expanding universe would cool like black body radiation. So in 1935, Robertson and Walker extended and developed the theory of Friedman and Lemaitre, as well as that of Robertson from 1929. In 1948, Ralph Alpher and Robert Herman made the first prediction of the cosmic microwave background radiation, estimating that it would be 5 degrees Kelvin, which turns out to be slightly off because, well, they didn't have as much observational data to get a more accurate estimate. Fred Hoyle. The term Big Bang was invented by Fred Hoyle in 1949 during a BBC broadcast. It was intended to be pejorative, and his tone was insulting. He preferred his steady state theory from 1948. He had developed this steady state theory to try to prevent there from being a Big Bang. But his theory also violated conservation of mass, energy, and momentum. He believed that having a beginning for the universe smacked of creation, and he said, quote, "The reason why scientists like the Big Bang is because they are overshadowed by the book of Genesis. It is deep within the psyche of most scientists to believe in the first page of Genesis." In 1956, George Gamow, quote, "Einstein remarked to me many years ago that the cosmic repulsion idea, that is his cosmological constant, was the biggest blunder he had made in his entire life." John Archibald Wheeler said, "Going into the doorway of the Institute for Advanced Studies Fold Hall with Einstein and George Gamow, I heard Einstein say to Gamow about the cosmological constant, 'That was my biggest blunder of my life.'" And Ralph Alpher, in conversation with Einstein at Princeton about problems concerning the apparent time span of cosmic expansion, a way to fix this was to reactivate the cosmological constant. Einstein did not like this very much, and, as I recall, said his introduction of the concept in his early work was a blunder. By the mid-1950s, Einstein's working on his ultimate set of field equations. He's using a non-Riemannian geometry. He has 4 field equations, 16 potential functions. He's found equations of motion, and he also finds that in his new theory, you don't have a gravitational constant, you have a gravitational function, and you don't have a cosmological constant, you have a cosmological function. The more compressed a universe is, the hotter it will be. Just as when you compress air, you're taking all the heat in one volume of air and putting it into a smaller volume of air, making it hotter. The same is true for the universe. If you compress the universe, it will get hotter. At an early epoch of the universe, there was light and matter, but the matter was so hot that it could not form atoms. It was all plasma. In such a scenario, light, being electromagnetic, cannot freely travel. It's scattered by all those free electrons and all the charged particles moving around in the plasma. However, when the universe cooled enough so that atoms could form, then light could traverse great distances across the universe. As the universe expanded, this light became highly red-shifted because the universe is stretching those light rays out. The light was stretched all the way down into the microwave spectrum. The cosmic microwave background now has a temperature of 2.725 Kelvin. Note that there is an earliest time beyond which observations of visible light are impossible. There's a barrier of scattered light. As you look farther and farther into the universe, there's going to be a wall you cannot see beyond. The only thing that can penetrate that wall that we know of are gravity waves, but no primordial gravity waves have been observed. In 1964, Penzias and Wilson discovered the microwave background radiation. Also in 1964, Stephen Hawking, for his PhD dissertation, proved one of his singularity theorems. He went on to develop a number of other singularity theorems, both by himself and with other people. However, his basic idea is that if you assume that gravity attracts on average, a fairly generous assumption, then if the universe is expanding at one point in time, it had to have had some singularity in the past. There is a Big Bang in the past under such circumstances. This was a big generalization of the Friedman, Lemaitre, Robertson, Walker theory that had assumed a homogeneous and isotropic distribution of mass through the universe. Hawking, Penrose, Ellis, they made no such assumptions. And so their theory is more general and implies that there must be a Big Bang. In 1979, Alan Guth, in an attempt to join quantum theory with general relativity, created inflationary cosmology, complete with inflaton fields. This gives an even bigger Big Bang. Since then, there have been all kinds of developments, including eternal chaotic inflationary models that have bubble universes. These are completely unscientific. Borda-Guth-Vilenkin published a theorem in 2003 in which they showed that any universe that is, on average, expanding is past incomplete. So it's more general than even Hawking's singularity theorem, and implies that inflationary cosmologies also have singularities. In other words, the Big Bang is unavoidable. Remember the cosmological argument. Whatever has a beginning has a cause. The universe had a beginning. The cause of the universe need not have a cause, since it is external to time and space, as well as matter, energy, and momentum. The cause of the universe is causeless, timeless, and immaterial. Our conclusion: science is not amenable to the study of the origin of the universe. A veil exists preventing us from making observations of the Big Bang. If a myth is a theory of origins, then the Big Bang is a myth on the level of any creation myth. And that brings us to the famous quote, "In the beginning was the Word." For Janot, what does space curve into? Janu threw this at me at the end of my last lecture, so I thought that I would address it for this lecture. The answer is nothing. Gravity is represented by metric relations between points on spacetime. Geometry is calculated from the metric relations. And so, what are the examples? Let's look at metrics on the plane, the Euclidean plane. The Euclidean metric is based on the Pythagorean theorem. The square in the length of distances between points is equal to the square in the difference of the x values plus the square of the difference in the y values. And you can depict that with the right triangle, and this is the well-known Pythagorean relation. We can change this into polar coordinates, which we'll need later in this exposition, in the following way. Notice that if the change in theta, d theta, is 0, then the change in length ds is equal to the change in radius dr, which makes some sense because you're just changing that radius a little bit. That's all you've done. However, if dr is 0, then you're moving on an arc of a circle. If r is fixed, change in r is 0, you end up with ds is equal to r d theta, which is the same as that famous formula from trigonometry, s equals r theta. S is the arc length at the edge of a sector of a circle, r is the radius, and d theta is the central angle measured in radians. So this formula is also consistent with Euclidean geometry. We can change that metric a little bit by throwing in a factor of 4 over 1 minus r squared, quantity squared. It's other than that, it's that times the same metric that we had for Euclidean space. However, this changes the geometry substantially. First note that the radius, if you start with a radius of 0, you can't make the radius any bigger than 1 because at r equals 1, that change in distance, ds, goes to infinity. Yes, if you start at the origin and move directly towards the edge of a circle of radius 1, the distance from the center to that circle will be infinity by this metric. Also, straightest possible paths under this metric are arcs of circles that intersect that boundary circle at a right angle, or straight line segments that go through the center and to the edge. A famous rendition of this so-called Poincaré disk was drawn by M.C. Escher with his famous angels and demons. In the Poincaré geometry, all of the angels and demons represented have exactly the same size. And it looks like they get smaller and smaller as you go to the edge of that circle, and there are more and more of them, infinitely many, as you go out. But from the perspective of the geometry of the Poincaré metric, they're all the same size. Notice if I take 3 of those straight paths, I can form what is called a geodesic triangle. The interior angles of that triangle are alpha, beta, and gamma here. Because these straight paths are little arcs of circles, the vertices are a little bit pinched, which means that the sum of the angles of this triangle will be strictly less than 180 degrees. An exact formula is given by the famous Gauss-Bonnet theorem. The angle sum, the sum of the angles, is equal to pi, or 180 degrees, plus what we call the total curvature. If k is the Gaussian curvature and dA is the element of area, t is the triangle that we've placed off here. If we integrate the curvature across the entire triangle using a double integral, then what we get is the total curvature. If the curvature is negative, as it is in the Poincaré disk, then the angle sum will be pi plus a little bit of a negative thing. That means it'll be less than 180 degrees. If the curvature is positive, then the angle sum will be greater than 180 degrees, and we can depict that by this sphere. We have a geodesic triangle drawn on the sphere, 2 90-degree angles down towards the equator of the sphere, and then another angle at the top, giving you an angle sum that is greater than 180 degrees. The metric that you need for this will have a fixed radius r is a constant here, but theta and phi are variable, and this gives you the metric that you would use on a sphere. I also want to give you some additional resources.